So today I'll talk about our work on this automated TCP testing. So this is joint work with my student Lisong, Zhao, and also with my colleague Sebastian Elbaum. So let's start with a quick question. So anyone knows what is the TCP congestion control algorithm currently used in each of those operating systems? So let's start with Linux. So how about Linux? Okay, great, it's cubic. Then next, how about the Mac OS? Yes, it's still cubic. And finally, how about this Windows 10? Okay, great, it's still cubic. Okay, now, so let's start with our motivating example. So this is an example of cubic. Okay, so suppose that we need to test whether this cubic is sometimes too aggressive. So what we do is, the first step, we write a testing script. So we create a very simple network with just one link, and with certain link speed and with certain packet loss rate. And then next, we run our script, and then we test the cubic in this network, and also we keep track of those state variables. For example, here we consider only two variables. First, CWND, so this is the congestion window size. And then second, target. So target, this is the expected congestion window size after one round trip time. And this target determines the aggressiveness of cubic. And finally, after experiments, and then we just check whether sometimes the target is more than twice of the CWND. If that happens, that means the cubic is even more aggressive than the standard slow start. Okay. However, so this test is very hard. The difficulty here is that even for this very simple example, we already have a very large number of possible combinations. Okay. And then it's impossible to test each of those possible combinations. So this is the type of work that we consider in our paper. So specifically, we propose this automated state space exploration to efficiently solve this type of TCP testing problems. So let's start with two concepts. So first, we define this parameter space P. So P is the network environment parameter space, so it contains all possible network environment to be tested. And for this example, so P just contains all possible combinations of the link speed and packet loss rate. And next, the state space. The state space, this is S, so this is a congestion control state space. So it contains all possible congestion state of a congestion control algorithm. And for this example, this S just contains all possible combinations of the CWND and also the target. Okay. So now let's consider this parameter space P and also this state space S. So for each point in this space P, so this corresponding to a unique network environment, so with some link speed and also with some packet loss rate. So now if we run TCP in this network environment, and then this cubic will visit a sequence of state in the state space S. Okay, so now as we choose more network environment in the space P, and then more state in S will be visited. So from here we can see that in order to solve this type of TCP testing problems, we do not need to test each network environment in the space P. And actually, we just need to find all possible regions of S that can be reached by a congestion control algorithm. And now for this cubic example, so this red region is the region where the cubic is too aggressive. So as long as we find if this cubic can be reached by, if this red space can be visited by cubic, and then we know that something is wrong with cubic. That means this cubic is too aggressive. Okay. So now finally, we are ready to define this automated state space exploration. So here we consider we are given a parameter space P. So this is for some testing script. And also we are given a state space S for some congestion control algorithm. The question is how to automatically choose those network environment in P in order to explore as many different regions of S as possible. Because once we have such an exploration method, and then we can use this method to test whether a congestion control algorithm has wrong behaviors or inappropriate behaviors by just checking whether the corresponding region of S can be visited or not. Okay. So now in this paper, we propose our method. So this is called automated congestion control testing. We call it ACT. So the goal of ACT is to explore as many different regions of S as possible instead of concentrating on just some regions. Okay. So basically, this ACT belongs to the class of feedback-guided random testing. So first, this ACT just randomly selects those network environment in P so that this ACT is scalable to a large space P. But this random selection is guided by some feedback, and so that ACT can efficiently explore different regions of S. And finally, our feedback is obtained from just the previous state coverage information, and it does not require any abstract model of P and S or the tested congestion control algorithm. So our ACT consists of 3 steps. So first, this random testing, and second, the parameter estimation, and finally, we call it parameter concatenation. The first step is very simple. We just uniformly, randomly select those network environment in P in order to have an initial coverage of the state space. Okay? So the reason that we choose this uniform random testing is because, and here we do not make any assumptions about P, we do not make any assumptions about S, and also we do not make any assumptions about the congestion control algorithm. So we choose this very simple uniform random testing as the first step. Okay. Now the reason that we need the second step is because we found that this uniform selection in P does not lead to uniform coverage of S. So this is because of the complicated nonlinear mapping from P to S. Okay? So this is why we propose the second step. We call it parameter estimation. So in order to explore those unvisited gaps and also unvisited corners. So first, let's consider a gap. So in the space S, we have this state S star. So this is a gap between the state SA and also state SB. Okay. So now in order to visit this gap, so what we do is first we find the network environment PA and PB corresponding to state SA and SB. And then we use what we call random interpolation to randomly find a point between the PA and the PB as this estimated P star. Okay, so our hope is that this P star can lead this congestion control algorithm to visit this unvisited gap of S star. Okay. So next, if we have an unvisited corner, so let's consider this S star so of the state space S. So we can see that this S star is below the state SC. Okay, so that means this S star has a smaller S2 compared to this state SC. So what we do here is that we find the network environment PC corresponding to this state SC. Okay, and then starting from this PC, we randomly select a network environment P star in the direction that decreases this S2. Okay. Now this direction can be estimated using the result that we obtained in the first step. Okay. So this is the basic idea of the second step. Okay. But what we found is that, so even after the second step, so some regions are still not visited if there is a correlation between those state variables. So for example, if there is a strong positive correlation between the state variable S1 and S2, okay, in this case, the P star estimated by the parameter estimation, so especially estimated by the extrapolation, actually will not visit the state S star. Instead, it will visit a state S plus. Okay, so from the initial state, finally reach only this S star. And I'm sorry, the S plus. So this is because this state S plus has not only a smaller S2, but also a smaller S1. So this is because the strong correlation between S1 and S2. Okay? So in order to solve this problem, so we propose this parameter concatenation. The idea is very simple. So this time we use both the network's environment PD and also we use the network environment P star. Okay? The idea is that we change the network environment from PD to P star in the middle of an experiment. And by doing so, okay, the algorithm will follow a different path in the state space. So it starts from the initial state and first go to the state SD. And then from SD back to the state S plus. Because it follows a different path, so it's more likely for this path to visit some unvisited regions. Okay? So this is the basic idea of our proposed ACT. And next, I'll show you some experimental result. Okay? So in our experiments, we test 5 real-world TCP congestion control algorithms. Okay, so this is for Linux kernel 3.10. So we consider cubic, so this is the current default one. And AMD, so this is the previous default one, so this is just TCP Reno. And also we consider HTCP, HSTCP, and also this Reno. Okay. The parameter space we consider is for a testing script that create only a single link. So this is a very simple but still very powerful network. And we consider the parameters including the packet loss rate, link speed, propagation delay, and random queuing delays, and also some application rate. Now for the state space, we consider those basic state variables. For example, we have the congestion window size and slow start threshold, the round trip time and the round trip time variance, and finally we have this congestion avoidance state. Okay, and also we consider some protocol-specific state variables. For example, we consider the target for cubic. Okay. Now we have two types of experiments. So first, the experiments for state space coverage, and finally we have experiments for the bug detection. Okay. So first, for the state space coverage, we measure the state space coverage by four different testing methods. So first, our proposed ACT, and second, the RAN. So this is just a simple random testing. And next, MAN. So this is the manual testing. So where we just manually select some popular network environment used in the previous studies. And finally, this SYM. So this is a symbolic testing. So where we use a symbolic execution engine to run this Linux TCP, but we represent those packet delays with symbolic variables. Okay. Now, in order to measure the state space coverage, we follow a very simple method. So what we did is we just divide this state space S into equal sized regions with a region size K. Okay. And then we measure the percentage of regions covered by each testing method. For example, and here we have the 3 regions out of 4 regions are covered, and therefore the coverage percentage is 75 for this region size K. Okay. Now this slide shows the coverage result. Okay. The y-axis is the percentage of regions covered by each testing method, and x-axis is for different region sizes from the minimum 1 to a very large region size is 1,000. And from here we can see that our proposed ACT always achieves the highest coverage, okay, so for different region sizes. Now in this figure, we do not show the results of symbolic testing. So this is because in our experiments, we have tens of thousands of packets. So that means in symbolic testing, we have tens of thousands of symbolic variables. However, this current symbolic testing is not scalable to such a large number of packets. Okay. Now next, in order to help you intuitively, the effectiveness of each step of ACT. So now let's consider a two-dimensional projection of the state space S. Okay, so here we consider only the state variable, congestion window size, and also the slow start threshold. So this is a two-dimensional projection of S. Okay. So first, after the first step, the random testing, the ACT covers those green state. Okay, as we can see that the coverage focuses on a small region of this whole state space. Okay. And then after the second step, the parameter estimation, we can see that now ACT also visits those blue states. Okay. But also from here, we can see a strong correlation between the congestion window size and the slow start threshold. As a result, so some regions are not covered, for example, the bottom right. Okay. And finally, after the third step, parameter concatenation, and now we cover more regions of S. Okay. So now you can see that the first step, random testing, covers only those green state, and the second step, parameter estimation, covers those blue state, and finally, the parameter concatenation covers those red state. Okay. So finally, I'll show you some result in bug detection. And here we consider 3 types of behaviors. So first, we consider a very simple generic behavior, and second, we consider the congestion window increase behavior of cubic, and finally, we consider the congestion window decrease behavior. Okay, the first test. So here we just check a generic behavior. It's very simple. We just test whether the congestion window size could be bigger than a very big number. So here we have is 10 million packets. Okay. So if this happens, that means something is wrong with this congestion control algorithm. And with this very simple behavior, and then we find one bug. Okay. So we found that sometimes those 4 different congestion control algorithms. The first one is the TCP Reno, second one HTCP, HSTCP, and also Vino. So all those 4 different TCP congestion control algorithms. So sometimes they set their congestion window size to a really, really big number. Okay, so as you can see that this is the serious bug of TCP. So, and also as you can imagine that we were very happy when we found this serious bug. But after we reported this to the Linux kernel developers, we were told that they just found this bug and fixed this bug. Okay. Next, I'll show you our experiments on the window increase behavior. So this is just the motivating example that we discussed at the beginning. So we just check whether cubic is too aggressive sometimes. Okay, so we found several bugs. And here, so this is one bug. So what we found is that if currently the TCP throughput is limited by the application rate, so this is called the application rate limited period. In this case, the cubic does not increase its CWND, but it still increases its target. And as a result, after those application rate limited period, the target will be much higher than twice of the CWND. So this is why after those periods, the cubic becomes very aggressive. So this is a bug. So this is actually a design bug that we didn't consider when we designed this cubic a long time ago. And finally, let's consider this window decrease behavior. Okay, so here we just check whether a congestion control algorithm reduces its CWND after a fast recovery. Okay, and also we found several bugs. Okay, and here, so this is one of those bugs. So we found out that sometimes AMD, the TCP Reno, and also HTCP, they just increases their congestion window size after a fast recovery. Okay, so what happens is that let's consider the time 5014. Okay, so at this time, when TCP AMD receives some duplicate acknowledgement, after that, the TCP or AMD reduces its congestion window size from 2 to 1 and also start fast recovery. But now, if this AMD detects that this fast recovery is unnecessary, and then the AMD will start to undo this recovery. Okay? But the mistake here is that the AMD will change the congestion window size from 1 to 4 instead of the original 2. Okay? So this is a bug that detected by our algorithm, and this is one of those bugs. Okay? And also we report this bug to the Linux kernel developers, and this is a new bug, and now this bug has been fixed. Okay? So finally, as a conclusion, so here we propose ACT. As you can see, it's a very simple technique. It's a very simple idea, but it's efficient, and also this is an effective tool for automated TCP congestion control, and this is mainly for the correctness testing, so not for the performance testing. Okay? And with ACT, we have found several the real-world Linux TCP bugs, and including some new bugs. Okay, thank you.
Okay, we have time for a few questions.
Hi. You mentioned somewhere in the middle of your talk that you have this ability of changing parameters or settings in the middle of the experiment. Do you have an example or where that was useful? Because if I look at the bugs that you found, none of them, they seem to fit into that category. So I was just curious about that. Thank you.
So for example, so this is one of the bugs that can be detected by this packet parameter concatenation. So this is where we change the network environment. For example, specifically in this bug, we change the application rate. So initially, the application rate is very small. This is why the TCP rate is limited by the application rate. And then after some time, we increase application rate to a higher number, and now we detect this bug.
Hey, Vyas from Carnegie Mellon. I have a question actually related to Christina's paper from NDSS, I think last year. I thought she was going to ask that, but I'll ask her. Okay. So actually, there's a very recent paper talking about like automatically doing modeling of congestion control, showing like security vulnerabilities in TCP congestion control, right? I thought you were going to say something about the talk about is there something different about the scope of bugs or the techniques or the coverage compared to that approach? I'd like to know a little bit more about that. Okay. I mean, both are cool works. I just want to know what's the conceptual difference between the two.
Okay. So here we consider so one type of bugs. So those bugs can be described or corresponding to certain regions of the state space. Okay. So our technique, this ACT, works for this type of bugs. So there are some bugs that our ACT does not help. For example, if this is a bug related to the specific TCP behavior at the packet level. So those bugs, this ACT does not work well. And for those bugs, it's better to use the tool developed by the Google. It's called packet drill. Okay? So our ACT is kind of complementary to the packet drill. Packet drill detects those specific bugs at the packet level. And our ACT can detect bugs corresponding to certain regions of a state space.
Okay. Thank you.
Okay, okay, yeah.
Okay, hello. So I'm Sam from Brown. I had a question. Okay, so here you have a perimeter space and you have a state space, and you mark the regions which the protocol shouldn't go to, and you mark those. Okay, this must be a bug. But can you actually use this approach to actually compare like congestion control protocols? So for example, at this loss rate or in certain ranges, this protocol has a better, like will give better throughput or something. Have you done this, or could you like actually extend this to comparing congestion control protocols and then finding out what, like for example, setting different parameters, find like which regions a certain protocol might be better than the other one?
Okay, so actually, so that is a very good suggestion. We haven't thought about that, but I think you are right. So this ACT can be used not only for this correctness testing, but also can be used for some performance testings to compare the performance of different congestion control algorithms.
Okay.
Yes.
Thank you.
Yeah, thank you for that.
Okay, let's thank the speaker, and this concludes this session.
Thank you.